This video is for Chemistry in the Earth System, Unit 1.5, Tectonic Plate Interactions. Today's essential question is, what is the supercontinent cycle, and how does it shape Earth's surface and life over time? Hello, baby birds! Today, we're going to connect the rise of the Isthmus of Panama, which we discussed in our last video, to the biggest pattern plate tectonics produces, the supercontinent cycle. Earth's continents don't sit still. Over deep time, they merge into a single supercontinent, and then later break apart, reshaping ocean circulation, climate, and even the evolution of life. Think of Earth's surface as a very, very slow puzzle that keeps changing which pieces touch. Scientists use this cycle to explain why we see repeating episodes of assembly and breakup, with enormous consequences for atmosphere, oceans, and organisms. To set the stage, the most recent supercontinent was Pangaea. Long before Panama existed, three ancestral continents, Laurentia, which is the Proto-North America, Baltica, which is the Proto-Europe, and Gondwana, which is a Proto-Africa, they all collided as plates moved. First, Baltica and Laurentia formed Laurasia, and then Gondwana merged with Laurasia to make Pangaea. These collisions helped build the Appalachian Mountains in the eastern U.S. Later, Pangaea began to rift about 200 million years ago, and the continents we recognize today started to take shape. Crucially, they're still moving now. After Pangaea's breakup, the Caribbean region evolved toward a configuration where the Isthmus of Panama eventually rose and sealed a gateway between the Pacific and Atlantic Oceans. That narrow strip of land would later reroute currents and connect the ecosystems that had been separated for tens of millions of years, exactly the kind of land-to-ocean replumbing consequence we expect from plate motion and reconfiguration. The supercontinent cycle has four repeating stages. Formation, in which continents converge over hundreds of millions of years. Second, supercontinent, in which all major land masses unite, dramatically altering global climate and ocean circulation. Number three, rifting, in which the supercontinent breaks, opening new ocean basins. And four, dispersal. Continents drift apart, setting the stage for a future cycle of convergence. The Isthmus of Panama emerges during the dispersal area that followed Pangaea's breakup, where microplates and arcs interacted in the Caribbean/Central American region. When the narrow land bridge finally did connect North and South America, it didn't just change who could walk where. It rerouted ocean currents, influenced heat transport, and helped reorganize climate patterns, exactly the kinds of system-level impacts the cycle predicts. But Pangaea was not the first supercontinent. Earlier supercontinents include Valbara, about 3.1 billion years ago, Rodinia, 1.1, and then Pannotia, about 600 million years ago. Their assembly and breakup episodes are reconstructed from very sparse ancient evidence. But the big picture is clear. Multiple cycles have occurred across Earth's history. This matters because each cycle reorganizes ocean basins and land connections, driving new climates and evolutionary pathways. Students, you, should see Panama's late Cenozoic land bridge as one of the many moments where changing geography reshaped biospheres. A smaller scale echo of what supercontinents do on a grand scale. When continents merge or separate, ocean circulation reroutes, sea level changes, and new habitats appear. That's why the supercontinent process is said to have profound effects on Earth's surface, atmosphere, climate, and organisms. As the Isthmus of Panama rose, it created a land bridge between North and South America and closed a marine connection between the Pacific and Atlantic Oceans. Biologically, this set the stage for the Great American Biotic Interchange, where species crossed the new land route. Physically, closing the seaway helped reorganize ocean currents. Your textbook uses the example of how plate-driven geography can ripple out into global climate. Exactly the sort of effect you would expect. For the Gunayala, the land-sea boundary is a living threshold, a place of relationship between peoples, waters, and winds. To finish up, we have a few key takeaways. Takeaway number 1, there are multiple cycles. Earth has hosted several supercontinents, not just Pangaea, each with massive consequences. Takeaway number 2, ongoing process. Plates are moving now. Today's map is just a snapshot in a long movie. Takeaway number 3, global impact. Reorganizing land and oceans reshapes currents, climate, and life. The Isthmus of Panama is your concrete example of how a geologic threshold can redirect oceans and reroute evolution, while the Gunayala lens reminds us that the places can be scientific systems and living relationships all at once. At this point, you should be able to generate a full and appropriate response to today's essential question. What is the supercontinent cycle, and how does it shape Earth's surface and life over time?